Hi, we're Group 1D on Nanotubes and Nanowires, and this is going to be Caroline Hildebrand and Emmi Skeans presenting. What are nanotubes? Nanotubes are a nanotechnology used in electrical applications. They are cylindrical tubes most commonly made up of graphitic carbon, a compound that forms a chicken wire-like structure. This structure can be seen in the figure shown. This unique structure makes carbon nanotubes incredibly strong. Some nanotubes have been found to be hundreds of times stronger than steel and up to 6 times lighter. These types of nanotubes are being used in airplanes, where weight is a serious stipulation. While originally carbon nanotubes were used only in rigid applications, recent scientific discoveries have made it possible for nanotubes to be flexible, opening up new doors in the field of electronics. Nanotubes can also be as small as 1 nanometer in radius, but be several centimeters in length, giving it the best width-to-length ratio in the field of electronics. The structure itself is made up of a 1-atom-thick piece of graphene that has been decomposed from carbon, which is rolled into tubular form. However, precisely how this tube is rolled changes the nanotube's properties drastically. The graphene nanoribbon can be rolled into 3 main structures named the armchair, chiral, and zigzag. These 3 different tubes change the material's band gap anywhere from 0 to 2 electron volts, as well as drastically change their semiconducting properties anywhere from effective semiconductors to metallic. It is important to note that these nanotubes can also be single-walled or double-walled, which also changes all of its properties. In addition to its structural properties, nanotubes also have other exceptional properties. They are fabulous conductors of heat because of their high thermal conductivity. They are also nonpolar, meaning van der Waals forces create a small attractive force between the tubes, making it easy to align them together, which is shown in the figure. Van der Waals forces are forces from non-covalent bonds and are not electrostatic interactions, but rather the residual attractive or repulsive forces between molecules. These forces are also what allow things like geckos to stick to walls and ceilings because of the nanohairs on their feet and the van der Waals forces at play. Nanotubes can also be great electrical conductors. Their conductivity is based on their diameter and the amount of twist they are given while rolled, as well as the structural properties that have already been defined above. Some forms of carbon nanotubes have been discovered to be 5 times more electrically conductive than steel, 15 times more thermally conductive than steel, and have a current capacity 1,000 times greater than copper.
What are nanowires? Nanowires are electrical components used in several areas of study, such as energy conservation, optics, electronics, and chemical sensing. To think of them simply, nanowires are just like normal electrical wires, but their small size allows them to perform optimally and efficiently. Nanowires are composed of numerous different materials like metals, organic compounds, insulators, and semiconductors. They have recently become a popular material because of their vast capabilities and benefits for a large range of studies and research. Nanowires, similar to nanotubes, are widely considered to be one-dimensional because 2 of their dimensions are of nano measurements. Shown on this slide is an array of nanowires. Nanowires are composed of solid crystalline fibers. The immensely small size of nanowires allows for optimal optical and electrical characteristics. Because of the simplicity of the nanowire structure, there are little to no defects. This lack of defects results in the efficient passing of electrons. This is one of the features that makes these nanowires surpass previously used electrical components such as wafers of silicon. Nanowires' length can stretch so long they can be seen by the human eye without equipment. The surface area of the nanowires can be specially treated to bind to biological materials. Also, their shapes have other benefits such as being used to produce LEDs or narrow beam lasers. These specific advantages might lead to making chips communicate via light instead of electrical charges. Due to the size of these nanowires, often they will take on quantum mechanical effects, which rely on quantum mechanics. One of these relied on quantum mechanical properties is quantum tunneling, which is explained in greater detail in the figure provided. This property allows wires made of nanotubes, specifically ones that are composed of carbon, to have high conductivity. There are a vast amount of applications for nanowires, such as quantum devices, MEMS, transistors, memory devices, field emitters, micro to nano-sized circuits, sophisticated composite circuits, optoelectronics, photon ballistic waveguides, and biomolecular nanosensors.
How do you fabricate nanotubes? There are three well-known processes when it comes to fabricating nanotubes: arc discharge, laser ablation, and chemical vapor deposition. Each of these has variable cost and time attributed to making a nanotube. The arc discharge method, like many other phenomenal scientific discoveries, was discovered by accident in 1991. In an enclosure filled with an inert gas at a low pressure, scientists were trying to produce fullerenes. They had placed two carbon rods end to end in the enclosure and drove a current through the rods with a high potential voltage difference. This action created an extremely high temperature, which vaporized the surface on one of the carbon rods. The deposition produced from this reaction contained the carbon nanotubes, as well as residual catalytic metals. This discovery led them to further purifying the deposition in order to solely obtain the carbon nanotubes. This extra purification step is the one major drawback of using the discharge method, as well as the fact that it destroys the original carbon rods. The second method for fabricating carbon nanotubes was discovered a little later in the decade than our first method, when it was discovered in the year 1996. This method is called the laser ablation method, which uses laser-aided vaporization. This technique requires a high-temperature reaction chamber and uses a graphite board instead of carbon rods. Instead of having an electrical current vaporize the board, a laser is activated and the laser vaporizes the graphite board. The gases in the chamber from the initial laser blast hold the key to forming the nanotube structures, so subsequent laser pulses are used to vaporize the remaining soot on the base of the chamber. The chamber vapor cools and condenses, which in turn forms the carbon nanotubes. These nanotubes are formed in ropes as the vapor cools, which just means that they appear to be bunches of carbon nanotubes held together by van der Waals forces. The laser ablation method can create different size nanotubes with different diameters and properties by changing the temperature in the chamber. The major drawbacks with laser ablation are the same as the major drawbacks of arc discharge, being that it destroys the source graphite and requires an extra purification step in order to obtain the carbon nanotubes. The third and most promising method of nanotube fabrication is called chemical vapor deposition. This method requires a sealed vacuum chamber, as gases are involved in the process. The process starts with some sort of metal catalyst substrate being placed on a quartz boat. The substrate is usually made up of one of three metals: iron, nickel, or cobalt. The variable amounts of each metal present in the substrate determines the diameter of the nanotubes that form. Once the substrate is placed, it is heated to at least 700 degrees centigrade. Once it has reached the desired temperature, which also contributes to determining the diameter of the nanotubes that form, gases are then pumped into the vacuum chamber in two phases, the process gas phase and the carbon-containing gas phase. Once the carbon-containing gas is pumped in, usually this carbon-containing gas is ethanol or ethylene, nanotubes begin to form on the ends of the substrate catalyst particles that have broken throughout this process. This is the most promising process because it can produce carbon nanotubes at a larger scale than the previous two methods, and it does not require a purification step.
How do you fabricate nanowires? Not widely known, nanowires can be grown on several different substrates using a process of vapor deposition. Vapor deposition does exactly what it sounds like, as it is a process where vapor goes through a series of steps in order to form deposits of solid nanowires. During this process, a variety of microbeads made of metals are deposited onto a surface. The microbeads of metal are scientifically referred to as catalysts, while the surface it is placed on is referred to as the substrate. Usually these microbeads are made of molten gold. However, other metals also work well enough to use depending on the wire's intended application. The nanowires seemingly grow on the catalyst when gas is added to the airtight chamber. Elements in the gas start to bond with the catalyst, and then more and more of the elements in the gas form bonds with the new bonds that were just created. This, in effect, creates wire-like structures that are known as nanowires. This process is illustrated in the images below with gold microbeads. The diameter and size of these nanowires can also be controlled by scientists. Changing the temperature in the chamber and size of the metal microbeads, catalysts can change the diameter of the nanowires, and changing the amount of gas and the length of time allowed for the gaseous reaction to take place can change the length of the nanowires. The template method can also be used to fabricate nanowires. This method itself is broken into two distinct techniques, one of which uses a hard template and one of which uses a soft template. The hard template technique is used to do exactly what it sounds like. It is a hard, usually some sort of polycarbonate or aluminum oxide template that is covered in little holes called nanopores that are used as a template to form nanowires. The pores are filled with the membrane of a monomer, and these membranes are then polymerized inside of the nanopores. Once the process is complete, removing the template leaves you with the desired nanowires. While removing the hard template, damage very commonly occurs of the nanowires. This process is illustrated in the STEM picture to the right. In order to control the diameter and length of the nanowires created from this process, a few more steps are needed. These steps include running a current through the metal template where the nanowires are being synthesized. The amount of time the current passes through the metal and the size of the current that is flowing through the metal changes the diameter of the nanowires. Changing the shape of the nanopores changes the length of the growing nanowires. The soft template method is made of exactly what it sounds like, a much softer template than metal. The template is usually comprised of surfactants or DNA. This method also uses monomers and relies on their interactions with the template and the chemicals around it to grow the nanowires. DNA is able to be used as a template because although it's considered soft, the chemical bonds of DNA are very strong, making it a sound structure that will not break when introduced to different monomers. The graphic shown in this paragraph gives a good visual example of how the DNA is used as a soft template in the fabrication of polyline nanowires. The soft template technique is sometimes preferred over the hard template technique because you don't always have to remove the template, and this reduces damage in the nanowires. Also, you can control the diameter and length of the formed nanowires with different oxidizing agents. Electrospinning is another technique used to make nanowires. This is a technique that uses electrical charge and electrostatic repulsion in order to create nanowires from liquid droplets. The droplets are placed on a spinning tip and induced with a high voltage stretched across their surface. This action causes a liquid jet to form, which is then further manipulated by electrostatic repulsive forces in the chamber. Once the liquid dries, thin fibers can be seen on the end of the spinning tip and can be collected and used as nanowires. Nanolithography is another method that is used to create nanowires. Nanolithography also comes with two different working techniques: dip pen nanolithography and E-beam nanolithography. Dip pen nanolithography uses an atomic force microscope to draw the nanowires on a gold surface. The tip of the microscope is used as the pen, while sulfonated polyaniline and polypyrrole is used as the ink. This technique can still control the diameter of the nanowire by controlling the amount of time the tip of the microscope is in contact with the gold surface. E-beam nanolithography uses electric fields to create nanowires. Electrons are fired in form a beam, which is focused without the use of a lens, but rather an electric field. This beam is fired onto a substrate and creates the nanowires. Although this technique allows for ultimate precision, this technique is not highly sought after because of its extreme equipment expenses, its fabrication time, and its relatively low output of nanowires.
Nanotubes in technology. Nanotubes have been very widely used in science and technology and appear to be really picking up speed in these past few years. Their size, strength, and electrical properties make them the ideal material to make many new devices, as well as upgrade the current technologies we have today. One of the first major technological updates that carbon nanotubes could facilitate is the birth of better pressure sensors. Nanotubes have specific resistances when they are formed, and these resistances can change based on changes in pressure in the area surrounding the nanotube. This resistance can be measured with a little Ohm's law calculation when scientists feed a known current through a nanotube that has a voltmeter attached across it. When pressure around the nanotube increases, the resistance through the nanotube decreases due to its particles being squeezed closer together. This discovery is very promising in the field of sensors, but nanotubes still need to be researched in order to discover how to stop them from stretching or compression so much during this process that they actually break electrical contact. Nanotubes also have seemingly limitless potential in the field of biology. However, much of the research is still in the preliminary phases. Some proposed ways nanotubes could be used are in the artificial synapses in the brain. These nanotube synapses could replace human synapses when someone has some sort of brain damage that leaves them paralyzed. This would connect the brain and the body again to allow for movement of real or artificial limbs. This is a very risky area of work as it involves irreplaceable nerves, brain surgery, and inorganic materials to be placed in the body and the brain. However, it is hard to argue that this research is not worth further pursuing. Nanotubes also specializing in having very small volume, but a decent surface area to compensate. Since batteries depend on surface area to hold charge, it is clear that nanotubes could be revolutionary in the battery industry. The current size of batteries could be maintained, but using nanotubes instead of the current technology could increase the surface area inside of the batteries drastically, increasing the charge capacity without increasing their volume. As more and more of the world lives on mobile devices, this could be absolutely essential to the world of electronics. Nanotubes are small, that's for sure, but it turns out they are so small that they can actually be created into thin sheets that are visibly transparent. The surprising fact about these thin sheets is that they are very simple to fabricate, and they are relatively cheap to manufacture. These thin, transparent, conductive sheets can be applied in so many of today's technologies, from television screens to LCD screens to plasma screens to the touch screens on our phones. The touchscreens on our phones can be made curved and somewhat flexible, preventing cracks and shattering screens as often. These thin sheets also don't use the rare earth elements that are currently being used in today's touchscreens, which means nanotubes could be saving the environment by conserving its rare earth elements. Speaking of saving the environment, these thin, transparent nanotubes can even be used to improve photovoltaic cells on the solar panels. Current solar panels are made with glass photovoltaic cells. These cells absorb the sun's light that penetrates the glass. However, a good portion of the sun's energy gets reflected by the glass. A thinner, transparent material, such as nanotubes, could reflect less light than the glass and could be increasing the yield of energy from today's solar panels. Nanotubes are also being researched as biomolecule markers. Carbon nanotubes coated in different chemical compounds can stick to certain cells, for example, a cancer cell that keeps rapidly multiplying and killing a patient. These nanotubes can be injected into the patient and will bond to the cancer cells. While the nanotubes cannot kill the cells, they can be detected easily with different imaging machines, allowing doctors to accurately see cancer's path in a patient and interpret their best plan of action. However, this technique has a huge consequence in that nanotubes have been proven to cause cancer in the lungs of rats and effectively will act as asbestos in the lungs of humans. The biggest thing stopping the progression of nanotube research is the unknown effects of the toxicity on the human body. It is clear nanotubes are not welcome in the lungs, but it is uncertain how they would get there if they weren't not being directly injected into the chest cavity. Nanotubes also have been proven to cause melanoma, a type of cancer that can attack the lining of tissue in some internal organs. The question scientists must answer is that do these risks outweigh the possibilities that are opened up to the world when nanotubes are used in technology?
Nanowires and technology. While nanowires have fewer current applications in technology/science than nanotubes, they are still making a large impact. Nanowires are used in complex ways, and they can also be used in simple ways. On the basic side of things, nanowires can be used as electronic circuitry components, such as field effect transistors, otherwise known as FETs. This is extremely important to the field of electronics as electronic devices get smaller and smaller. The circuitry that makes up these devices must somehow also be scaled down, and nanowires are providing a sound path to do so. Nanowire FETs can also be customized for the specific characteristics needs of a device by manipulating the active channel in the nanowires. Also, since nanowires can be controllably doped, they make for an easier material to work in comparison to the larger circuitry options. Nanowire FETs are very commonly used in small sensors that detect things like electrical properties, environmental properties such as temperature and humidity, motion and movement, and light sensors that sense light beyond the capabilities of the human eye. Along with being light sensors, nanowires can also be used as a way to direct the light, as it acts as a great waveguide. While nanotubes have proven to revolutionize the solar industry by providing a less reflective structure, nanowires are also playing a part in the photovoltaic advancement. The nanowires themselves, when surrounded by the right materials, can act as a photovoltaic cell and collect energy from the sun. This is being used as a breakthrough technology in solar cells and is also being used to collect energy in other ways. Nanowires are being used to collect energy through sound, movement, and other waveforms found in the world. Conclusion. Overall, it is clear that nanowires and nanotubes are absolutely amazing technology devices that are helping shape the ever-growing electrical world. Nanowires and nanotubes will surely help improve technologies now and provide a solid basis for designing technologies of the future.